Okay, I guess I start then.
Yes,
Okay.
please go ahead. Floor is yours.
Thank you. Yeah, my name is Arthur, and together with Hugo from HPE, we will present the SAPPAN innovations in DGA detection. So to get started, let's first introduce what the DGA is. So let's first have a look at traditional botnet communication. Usually a bot has two approaches here. It will either use a fixed IP address or a fixed domain name in order to get the IP address of the C2 server and thereby to communicate with the botnet herder. So from the perspective of the botnet herder, this has a major drawback, as the defender can easily block this connection establishment attempt once these values are known. So this is why modern botnets rely on domain generation algorithms and short DGA. And DGA is a pseudo-random algorithm that generates a huge amount of domain names, which are subsequently queried by the bot in order to obtain the command and control IP address. The botnet herder usually only registers a small subset of the generated domains. Thus, most of the queries result in non-existing domain responses, and only the one query results to a valid IP address for which the botnet herder registered the domain in advance. And he is capable of this because he knows the generation scheme. These NXDs can be analyzed within a network in order to detect DGA activity, but the non-existing domain responses are not only generated by bots, but also are caused by typing errors, misconfigured software or outdated software, as well as by the intentional misuse of the DNS, for example, by antivirus software. So in the past, several DGA binary classification classifier have been proposed, which try to separate these malicious domains from the benign domains. And these classifiers also achieve high accuracies. And this is called the DGA binary classification task. And going one step further, it might be desirable to not only detect DGAs, but also to attribute them to the domains, to the DGA that generated them, in order to allow for targeted remediation measures. And this is, of course, more difficult as a binary classification task, as there are already over 92 DGAs now. So in SAPPAN, we had the use case of DGA detection, and we focused here on a research-driven approach. In total, we already published 7 papers in the context of DGA detection, so only on the context in DGA detection, and an 8th paper is already under review, submitted and under review. And however, we not only focus on the research, but we also keep in mind that we want to apply it in the real world. And therefore, during our research, we ensured that the classifiers are real-time capable and scalable. And we also put integration efforts and integrated our research already into existing security information and event management solutions. So here on the right side, you can see a word cloud, which contains a lot of aspects we have covered during our research. And in the following slides, I will try to represent selected results from our research in 1 or 2 slides each. So in SAPPAN, we started with the DGA binary classification task. That is to say, we wanted to separate the benign from the malicious domains. To do this, we proposed a neural network classifier, which is based on the residual neural networks. And here in this figure, you can see its structure. And these so-called ResNets, they introduce so-called skip connections. You can see it here, which ease the training and counteract the vanishing gradient problem. We compared our binary residual neural network-based classifier with the state of the art, and could show that our classifier reduces the false positive rate and works very well. And during this study, we also focus on 2 different aspects. The first aspect is generalization. And here we train a classifier in one network and then evaluate the classifier on real-world data from a different network. And we could show that the classifier generalizes very well, and therefore the classification could actually be outsourced as a service. The second aspect we investigated was whether the classifier is time robust. So we trained the classifier on data from one point in time, and then evaluated the classifier on data even which was captured 17 months later. And we could show that the classifier is time robust. And of course, the false positive rate slightly increases, but was still manageable. And of course, if you want to have a classifier that works best, you would use still frequent retraining. And to ensure its real-time capability, we tested the classifier in a large real-world network and classified a whole 1 month recording and showed its feasibility. We then continued with the multi-class classification task, and here we wanted to attribute a domain either to the benign class or to any DGA that is known in the training data. And here we also proposed a resonant-based classifier, but this time it was deeper. It consists of 11 residual blocks. And here on the right side, you can see a confusion matrix, which is used to visualize the performance of the classifier. So at the top left corner, you can see the benign class, which is separated very well from the other classes. And on the y-axis, you can see the true label of a sample. And on the x-axis, you can see the predicted label of a sample. So a perfect classifier would actually yield an identity matrix. And what you can see is that the classifier is working remarkably well, as most DGAs are detected with high confidence, but there are still some outliers. For instance, here, this is the DNS benchmark. And the reason for this outlier, for instance, is that they use data source. So we used the DG Archive open source intelligence feed, and it contains only 5 samples for this specific DGA. And since we used 5-fold cross-validation, we trained a classifier on 4 samples and tested on the left out sample from the training set. And if we classified this one sample wrong, then the whole score of the specific class degrades to 0. Again, we did a comparative study with the state of the art and could show that our classifier requires 30% less of training time. And we could also show that we achieve an improvement of over 5% in macro of 1 score, which corresponds to the fact that our classifier is able to detect several classes with high confidence, which the other state-of-the-art classifier cannot correctly detect. And again, we tested this classifier in a 1 month recording and could show that it is real-time capable. The 2 classifiers I have presented you are deep learning based, and therefore they heavily depend on the used training data. And as you could see on the example of DNS benchmark, the sample distribution is heavily imbalanced. This is why we investigated in SAPPAN whether it is beneficial to include underrepresented DGAs into the training set. And for this, we conducted a comprehensive study, and for both classification tasks, we showed that it is beneficial to include those samples. As for the binary classification task, we could improve its detection performance by over 10%. And in case of the multi-class classification task, we could show that for 22 of the 46 weakly represented classes, we could reach an F1 score of over 90%. And for 11 classes, even an F1 score of over 99%. The major important aspect here is that no significant influence on the classification of the well-represented classes could be measured. So it's definitely beneficial to include them. On the other hand, if we would omit these samples, then in a real world, the classifier would still have to deal with them because they can appear in a real world network. And therefore, to model this, we did an experiment in which we trained the classifier on samples of the well-represented group, and we classified samples on the weakly represented group. So this is the classifiers we left out, and this is the classifiers we trained on. And as you can see here, a huge fraction of samples is actually classified to the benign class if left out, and this corresponds to the fact that an intrusion detection system would miss these samples entirely, and not that they are just classified to a different malicious class. So again, it is definitely useful to include weakly represented DGAs into the training set. Even though the proposed classifiers achieve high accuracies, they are still deep learning classifiers, and thus they behave like black boxes. And therefore, it is difficult to evaluate their line of reasoning, as this results in a lack of confidence, because it is unclear why a sample is either classified to the benign class or why a classifier classified a sample to either one of the DGAs. So this is actually also the reason why security analysts prefer simpler solutions such as decision trees or even rule-based systems. And to counteract this issue, we developed two approaches in SAPPAN. The first approach is based on a visual analytics system, which tries to provide understandable interpretations for predictions of deep learning classifiers. And I don't want to go into detail here, but the main idea is that we cluster the activations of the model's neurons, and then we leverage decision trees in order to explain these clusters. The second approach is based on the idea of explainability by design. And for this purpose, we developed a feature-based classifier, Explain, which is based on random forest, and we evaluated it, and it's competitive and contextless. And the main idea here is that by using feature-based approach, we can easier interpret the predictions as they can be traced back to characteristic of the used features. Again, on the right side here, you can see the confusion matrix, but this time it's a combined confusion matrix. So the upper left part is dedicated to the feature-based approach, and the lower right part is dedicated to the deep learning-based approach. And what you can see here is that it seems that the deep learning-based approach learns similar features as we have studied for the feature-based approach, as the classifications are very similar. And in total, we studied 136 contextless features, 42 of which we gathered from related work, and 94 were newly developed. These features can be divided into three different groups. The first group are linguistic features, and they, for instance, count the numbers within a domain or compute the foveal ratio. The second group are structural features. This is, for instance, the domain length. And the last group are statistical features, and they, for instance, compute frequency distributions of certain n-grams or the entropy. And again, we tested the classifier and ensured its real-time capability. As Martin have said in the previous talk, a big aspect in SAPPAN is the privacy-preserving intelligence sharing. And here we wanted to increase or improve the detection performance of a classifier by collaboration. Of course, we can't share raw data because it contains sensitive information. For instance, if we would share the domain names of one network, then of course it might be possible to reconstruct the browser history, for instance, of an employee within a network. And also, not only the raw data contains sensitive information, but also the models may leak sensitive information. For instance, they can be attacked by a membership inference attack, and then you could reveal or try to reveal training samples used in the model. And therefore, in SAPPAN, we improve generalization performance by sharing intelligence at different stages of the model training, and we do this in a privacy-preserving fashion. So the naive approach would, again, be the raw data sharing. Here we propose to use different anonymization techniques and also the application of Bloom filters, for instance. The second approach is after the model training. And here, for instance, ensemble classification can be used. So every party trains an own model, and then they do combine the models, for instance, by majority voting in order to come to a final result. And another approach here is feature extractor sharing. And here we only share parts of the model to which we refer to as a feature extractor. And the main idea here is by sharing less information, we have less information leakage of sensitive data. And of course, information sharing is also possible during the training of a model. And for instance, in federated learning, we share the updates of the weights. And in the teacher-student approach, we train a student classifier based on the predictions of teacher classifiers. And we conducted an empirical study, and there we could show that the feature extractor sharing and federated learning perform best. And there we could show that we can achieve a significant reduction in false positive rate by up to 50% compared to a single party approach. And here we also ensured that the reduction rate of the false positive rate correlates actually with the increasing number of parties that are collaborating. And thereby we could ensure that the collaboration actually works. And we also conducted a preliminary privacy utility trade-off study in which we could show that, for instance, for the federated learning approach, we can ensure the protection of the privacy with a manageable overhead. Another thing we investigated in SAPPAN is privacy-preserving classification as a service. The reason for this is that for well-performing classifiers, real-world training data is mandatory, but this is always not available for everyone. So, and also a second aspect would be if you would, for instance, like to do DGA detection on resource-constrained devices such as smartphones. And here the main idea is that we have a client that is the data owner, and he or she wants to classify or get a prediction for a data item, a domain name in this case, and this is sent to the model owner. And of course, this cannot be sent in plain. As I said, the model owner could reconstruct, or he knows then what the client is visiting for websites. And also the calculations done on this side should not be leaked to the client, as the client could try to steal the model or could try to get information about the used training data here, and should only receive the prediction. And in related work, several privacy-preserving machine learning frameworks have been proposed in the past. And the naive application of these frameworks to existing DGA classifiers resulted in an additional cost of inference latency of 13 minutes, or even a communication effort of 234 gigabytes, which is required for a single inference. So we conducted again a comprehensive study in which we analyzed different homomorphic encryption and secret sharing based approaches to secure multi-party computation, and we proposed several model simplifications. And these model simplifications result in a reduction in inference latency of up to 95% and a reduction in communication complexity of up to 97%, while obtaining an accuracy penalty of less than 0.17%. Of course, these numbers I mentioned here are worst case scenario numbers. If we apply these model simplification on the average case, we obtain inference latencies of several seconds or even under 1 second, but still this is not enough for real-time classification, and thus still future work is required. Now I briefly mentioned current and future work. And in the future work, we want to improve the robustness of the DGA classifiers against adversarial attacks. And in a preliminary study, we already showed that the NX classifiers are more robust against adversarial attacks compared to classifiers that are trained on resolving traffic. Here you already get the advantage of using NX data, as for instance, the activity of DGA is detected earlier than it can actually partake in any malicious action, as it's still trying to resolve to a valid command and control server IP. And also the order of magnitude is less than the order of magnitude of full resolving traffic. And in future work, we want to generate different adversarial examples and use them in different training sets to perform adversarial training in order to improve then the robustness of the classifiers. Further, we already developed a new DGA detection system, which is in the paper, which is currently under review. And but in another real-world experiment, we already could show that we could detect 6 unknown DGAs and 1 unknown seed of a known DGA. And our goal here was to develop a new DGA detection system, which is adaptive and also, of course, real-time capable. And the final goal of our research would be combining all research together to a single detection system. So this was the quick summary of several selected results. But maybe a short, very, very short overview on the implications of our research. So we improved the state of the art in various aspects. As I said, we have published 7 papers on DGA detection. 1 is currently under review. And we published the binary and multi-class detection model. And also the explain classifier is open source available. It is well documented, so you could actually try it out. And it contains everything, the whole classification pipeline, including hyperparameter optimization, feature selection, and so on. And our classifiers are, as I said, real-world applicable. And we also integrated our research already in existing CM solutions. So here you can see a screenshot of one integration of one partner of us. And the goal of this integration was, of course, to improve the detection performance and also reduce the false positives and providing explanation for predictions. And another integration is now presented by Hugo from HPE. And yeah, Hugo, please.
Okay. Okay. Hello. Can you hear me, right?
Yes.
Yes.
Okay. Okay, so yeah, in HPE, we wanted to implement what Arthur has been describing, the DGA classifier from SAPPAN. And the idea was that we needed to design the solution to integrate seamlessly with our existing infrastructure and platform to prove that it's real world applicability, right? So we have a flow processing pipeline platform where we receive a lot of observability data from different sources, including web proxies, firewalling devices, and a number of other sources. So we wanted to apply the SAPPAN DGA classifier to one particular kind of data, which is from web proxy, which has the required request URL property in the data that we could classify to determine if it is malicious or non-malicious domains. Okay, so in our stream, we have what is in the screen, a number of streaming events that have with timestamp, the source IP address, the destination IP address, and the request URL that the client tried to attempt from inside the HPE network to outside. So you can see different examples. These are mock-up examples. And then the idea is that the classifier, that the DGA classifier is not truly stream based. So what we have to do is to create tumbling windows of a fixed size, for example, 10 minutes, where we will be accumulating events from this stream to go to process into the DGA classifier at regular intervals. So for example, in the screen, you can see that we can build 3 different input windows every 10 minutes that will have a number of different events inside. And then we send them independently to the DGA classifier that will then reply with the results of which events of them were classified as malicious or non-malicious. And finally, we will be storing these results into a store, a document store in this case, for further visualizing by our analyst team in using a tool called Grafana. Now, this DGA classifier, initially we implemented it with a very simple model that was given by the team from Arthur with a mixed result, but then they provide us with federated model, which greatly improved the false positive result that we were getting initially. So definitely the federated model proved to be better than with our real data than the basic models. And another thing that I wanted to highlight is that Grafana is actually an observability visualization tool, typically used for metrics of running system. But we wanted to use it because our analysts are very used to this tool already in the company, and we wanted to reuse that know-how as a simple extra dashboard instead of having to deploy a completely new tool for them. So we are showcasing here how to integrate this completely into our workflow using the DGA classifier under the hood. This was also designed to be pluggable and modular into our platform, so we don't have to modify or stop the production flow passing by on the system. So we also managed to very easily integrate it like that. In our platform. It runs in parallel to our streams, providing data to Grafana. So I want to quickly share my screen now because I wanted to show. Okay, let's say that. Okay, now I probably will be able to. I want to show you the dashboard that we created for this application. Let me know when you can see my screen.
Yes,
we can see it.
Okay, so this is Grafana. We have this dashboard. We created this dashboard from scratch for the application of the DGA, and we created a number of panels that are in real time getting data from the document store that we chose for storing the results of the classifier. So first on the left, we have this malicious domains dashboard, panel that shows all the detected malicious domain from the DGA at different windows. And the number of sources, IP addresses that reference this domain at the time, right? And on the right, we have the opposite, which is non-malicious domain, and which usually are much many than the malicious ones, right? And then in the bottom panel, we can see details of both the malicious domain found and the non-malicious domain found in real time. So, for instance, I'm right now showing you results from the last 12 hours. This is constantly running for several weeks now. So in this case, the DGA was able to find these 3 malicious domains. This is the confidence that the model provides as well. By the way, I forgot to mention that we are using the binary classifier model here, not the multi-class. We also tested that one, but we wanted to keep it simple for the first proof of concept, like you are seeing here. So this is the confidence that comes straight directly from the model at different times. So these are 3 domains, for example, that were found in the last 12 hours. And in here in the details, for example, if I open this one, newspring.kr, we can see from which IP address this domain was tried to access in our web proxy logs, the company-wide. Okay, so if I do this for the APAN, it's the same. I can see here. For the case of non-malicious, I also have the same sort of information. So, for example, if I click just randomly one, I also can inspect it. So the idea here is that the analyst officer employee that is monitoring constantly the company can have this dashboard in running in real time, and then when the domains that are clearly malicious, either by confidence level here or by visual inspection, can quickly go here and or retrieve the IP address that was trying to access that, and then use other systems that we have in place to track down the owner of this IP address, the location, and then further investigate quickly what could be generating this malicious traffic, right? So for instance, I can here go even more, like 2 days, for example. And I would be getting more data from historic data. You see, so here we have even more domains like these ones that look very suspicious, right? And again, I can inspect here from where they come. So this is very convenient for us. We definitely are looking forward to a more adaptive result, because there are a lot of, as you can see, the other sort of domains that we see, there are a lot of mistype domains that sometimes get classified as malicious. Sometimes, actually, this is what improved much more when using the federated model. With the basic model, a lot of typos were classified as malicious with very high confidence, but this reduces a lot after the federated model. So yeah, this is an interactive tool in that regard, because it's constantly getting data from the service that is running, and we can scale it as much as we need. We found that it's actually quite capable, as Arthur mentioned. It's able to process several thousand domains per request in a very short time. So the window that we chose here is 15 minutes. So we create 4 classifications per hour, basically. To don't crow or pollute too much this visualization. But this feed that the web proxy feed is having around 2,000 average events per second in the source stream. So we could apply this to bigger volumes of feed, for example, not only for the web proxy, but also we could implement it in the firewall observability data, where we could resolve with domains are not being resolved, sorry, and pass it through the classifier as well, and display it like this. So yeah, I can say that this classifier is very easy to integrate in our platform. This was it proved to give a good interesting result to go in specs, and more importantly, it greatly reduces the time that the analyst has to be looking into this data, because it's just a very small sample of data that they have to go inspect. So for example, for the last 30 minutes, there was no suspicious domain in this case. So it's very tidy in that regard. So yeah, I think that is what I have to show here. If any question, I'm gonna give control back to Arthur now.
Well, yes, this concludes the talk, I would say.
Thanks, thanks, Arthur and Hugo. So there is some questions from the audience. So if you can try to answer it. So in the chat.
Yes, so the question from Pavel, when I try to give these 3 malicious domains to VirusTotal, they are all claimed to be safe. What do I miss here? Yeah, maybe they are false positives. So even though the accuracy is like 99.99x%, of course, the false positive rate is at 0.0001.
Maybe I have another explanation.
Yes, they are maybe not trained on the so we don't had the HP data, so they're not trained on HP.
No, I mean in VirusTotal usually people submit domain names that they know that are used for hosting, for example, some malicious content or things like that. But please be aware that these are not non-existing domain names. These domain names that are generated by algorithm, they are not registered yet. Attacker register only some of them to actually let the botnet to connect to command and control server. So this is a non-existing domain name, and therefore probably the virus does not know it.
Exactly.
Okay. So thank you, Martin, for the answer.
I wanted to also complement that answer that in the regard of training data, it's true that it's a big challenge to get training data, because first of all, we don't have it. We don't have data to say this is malicious, this is not malicious with our data. And I expect many other companies to not have this sort of data. That where we see the value of the federation is that we can make a model that works for most of us without having to have big data ourselves. And we were thinking internally as well at some point that this dashboard I showed you could incorporate some sort of feedback loop from the analyst, like when the analyst, which is the actual human that goes to check those results and verify if they are of concern or not, they could be providing like with a button or something. Okay, I went to check this and I found that it was not malicious, or I effectively found that it was a domain that was used for a C2 machine, and so on. So there is definitely room for improvement to provide or to build training data that we could later use for retraining the model, right? But yeah, it is. I want to acknowledge that it is a big challenge to not have training data in our organization.
Okay. Thank you, Hugo. So I think we're a little bit behind time. So the next thing is to have a quick break.